Okay, welcome back everyone. In this video, we shall proceed our discussion towards earlier we were talking about, mixed reactors. We talked about a CSGR and a batch reactor. Now we're gonna move our discussion towards plug-flow reactors. So before we start talking about plug-flow reactor, I have to clarify that plug-flow reactor, also known as a PFR, is an ideal reactor. Okay, is an ideal reactor. Keep that in mind. And what do I mean by ideal? Whenever you talk about an ideal reactor, you're talking about the fluid mechanics, the mixing, the velocity profile. The velocity profile is ideal. Most tubular reactors that you're going to find in industry, they're going to show some level of non-ideality. Okay, everything is going to show some level of non-ideality, but in order to first start a design, you have to start with something ideal, hence PFR. First off, we need to discuss what is the meaning of plug flow. What do you mean by that? What do you mean by plug flow? All right, so let's demystify that. Plug flow is basically means uniform velocity profile. Uniform velocity profile. And if you've taken a fluid mechanics or transport phenomena class, you know that a laminar flow gives a parabolic profile. We need a uniform velocity profile. Okay, we need a uniform velocity profile, and in order to achieve uniform velocity profile, you need turbulent flow. Okay, you need turbulent flow. All right, hold up, let me just give me 1 second. We shall just move this to the side. Okay, make some room for the other discussion. Turbulent regime. And what else? Uniform velocity profile. Every particle, if the velocity is uniform, every particle spends the same amount of time, spends equal time in the reactor. Okay. And another important implication of plug flow is no back mixing. No back mixing. Now you guys are probably wondering, what the hell is back mixing? I am throwing these terms at you, but what do they mean? Okay, let me just show you, intuitively speaking. So if you have a CSTR and you dump a stream into it, some of it is gonna go in, swirl around. The swirling back is called back mixing. Okay, the particle, if I were to trace this, let me zoom in a bit. So let's say you have particles coming in. Okay, this is their trajectory, and instead of following a straight trajectory, they're gonna swirl back. That is back mixing. And in a plug flow reactor, we have none of that. We assume there's none of that. Okay, we've talked about the fluid mechanics. Now, before we proceed towards the mole balance, I want to show you intuitively the extremes that you're going to encounter. Okay, that's my attempt at drawing a tube. So you have stuff going in, stuff going out. In laminar flow, if you guys remember, in laminar flow, once you solve the Huygens-Poiseuille's law for Newtonian fluids, you're going to have a parabolic velocity profile. So the velocity is at the peak. The velocity is highest at the center. And as you go towards the edges, of the pipe, velocity decreases. This is laminar flow. And as you guys can probably see, the particles that are going to be at the center are faster. All right, particles at the center are faster. But particles at the edge, where the velocity is slightly slower, are, as you guys can probably wonder, they're slower. Okay, they're slower. So therefore, both of these particles have different residence times. You have a difference in residence times due to the velocity profile. Different residence times. And you don't want that. You want all of your particles to spend the same amount of time in your tube to get good conversion. Okay, it's not ideal if you have like one particle that's the particles at the center are faster, so they're not going into the same conversion, etc., etc. So just to keep things organized and keep things easier to analyze. Now let me just copy this and show you how the plug flow regime is gonna look like. Okay, I want the picture only. Sorry, hold up. Give me 1 second, we're having some technical difficulties. Copy, paste. There we go. Alright, so let me just get rid of all this stuff that I've drawn here. We have our tube once again, and now the plug flow regime is gonna look something like this. So the shape actually looks like a plug. The shape of this velocity profile looks like a plug. If you've ever like a plunger in a syringe, the shape looks like a plug. Okay, now every the molecules at the center and the molecules near the edges, they're all spending the same time. Okay, same residence time for each particle. Okay, let me just write that down, and now we shall move on to the mole balance. We need to derive the mole balance for a plug flow reactor. And all of these plug flow reactors, oops, my tablet once again is giving me a hard time. So the assumptions are going to be as following. Like we said, we're obviously going to write our mole balance on steady state. All these tubular reactors are operated at steady state. We're going to have no axial dispersion. What do I mean by that? No axial dispersion means that your concentration, your rate of reaction, your temperature, these properties, these variables are not functions of the radius. They're not functions of the radius. They do not, it doesn't matter if you're at the center or if you're at the edge. You're gonna have no variation axially. All right, that's the meaning of no axial dispersion. And all right, and we already know that there's gonna be no back mixing. So let's derive our mole balance, shall we? All right, so I'm gonna take the entire tube, but obviously it's not feasible to write the balance on the entire tube. Therefore, we're gonna do a very simple shell balance. I'm gonna take a small differential volume of size dV, and there is reactant coming in. Okay, reactant is coming in at dV. Sorry, I'm just gonna call that, it's just coming in. Okay, it's entering your differential volume, and it is leaving with some change. Okay, and this change can be either positive or negative depending on whether you have a reactant or a product. So for now, I'm just doing the reaction A goes to B, a simple isomerization reaction. Okay, let's see. And also there's going to be a net generation term inside. There's obviously going to be a net generation term inside this volume. So let's see what I get. In minus out plus gen equals accumulation. Okay, and obviously I'm not dealing with any accumulation since I'm operating at steady state, so that goes to 0. And my inlet stream is FA, my outlet stream is FA plus DFA, and that DFA is this DFA accounts for the fact that either the species is going to be consumed or it's going to be generated due to a reaction, and this shall be accounted by the rate expression multiplied by the differential volume. All right, so let's see what I can get. Boom boom, negative DFA equals negative RAdV. Now this is just some simple algebra. I get DFA divided by dV equals RA. Now this, according to H. Scott Fogler, this is the design equation. This is the mole balance according to Fogler. Okay, and in some other textbooks, they play around. They replace dV as the cross-sectional area times dz. So some textbooks are going to do that. In Fogler, that's not the case. So don't worry about it. And now, once you want to size the reactor, you need the boundary conditions. You need one boundary condition. And the one boundary condition you need are going to be your inlet conditions. Your inlet conditions are going to be your boundary conditions. So which means at V equals 0, FA is going to be equal to the inlet flow rate, right? Makes sense. So once you integrate this, what you're looking for is the volume. Okay, and as you can see, once again, in order to get a desired, if you want to go from FA in to FA out, if you want to go from a certain inlet molar flow rate to a certain desired outlet flow rate, you need to know the functionality, you need to know the rate law. Once you have the rate law, integrating this expression is just a Calc 2 problem. So the volume of the PFR, is going to be how much you're sending in, FAN once again, FAN, give me one, FA, how much you want, 1 over negative RA. You need to know, you need the kinetics in order to size this reactor. You need the kinetics, and this right here, ladies and gentlemen, is the design equation. This right here is the design equation for a PFR. Okay, well done. Now, all right, just to give you a recap. Plug flow. PFR is an ideal reactor, just like well-mixed CSTR is an ideal reactor. The ideality comes from the fluid mechanics, the velocity profile. All right, the ideality depends on the fluid mechanics of your reactor. We talked about plug flow, uniform velocity profile. Okay, and in order to achieve uniform velocity profile, you need to know that you need to operate in the turbulent regime, and an implication of the uniform velocity profile is that every particle spends equal time in the reactor. Okay, and no backmixing. Backmixing was shown as, the extreme example was a CSTR. A CSTR is an extreme example of backmixing, and we have none of that in a PFR. All right, we compared the laminar profile, how the particles at the center are faster than the particles at the edge, laminar flow, versus plug flow, where particles at the center and the particles at the edges spend the same amount of time in the reactor. Okay, and yeah, then before we derived our mole balance, we listed our assumptions: steady state, no axial dispersion, no backmixing, and boom boom boom, in minus out plus 10 equals 0, and we got our differential equation. And in order to integrate that, we need to know the rate expression. This is where the knowledge from kinetics comes in. And yeah, our design equation. Thank you very much, guys. I hope this was helpful.